Okay, what constitutes a hybrid car, a hybrid or an electric car? Let's see what components there are there. So this is a typical electric car. First, you have the floor of the car filled with batteries. You have cells which make up modules, which make up a huge battery pack. Next, you have the controller, the battery management system, BMS, as you would have studied in your classes. You also have an inverter because you cannot use, say, 48 volt or 300 volt architecture for, say, your cabin lamps. So it will burn, it will not take in. So you would need a converter to convert it from 300 volts to usable DC 12 volt voltage. That is why you have an inverter. Next, you have the motor, which actually drives the car. That's where the major amount of battery voltage goes on to. Next, you have the onboard charger of the vehicle, which charges the batteries. This charger is just a port, you could say. And you would have an external charger which is connected to your grid at your house, and then you have a long cable which comes up to the charging port of the car. It's similar to your smartphones. You have a charger connected to the outlet, you plug it into your phone, and it charges. And automatically it switches off when it reaches 100%. But when your phone takes, most Samsung's fast chargers take around an hour and a half to charge around 4,000 milliamperes. This would take, for the size of car, say a Nexon EV, it would take around 8 to 9 hours to charge the entire car. That is from the regular outlet in your house. AC fast charging, AC slow charging, I'm sorry, AC slow charging. Then for most cars, they do not require a transmission, but you might have one reduction gear, probably first. You might have one reduction gear, which is why you have a transmission. Then you would also have an auxiliary battery, which would not be lithium ion, which would be lead acid to control your, again, as I said, lights, wipers, brake lamps, all those systems which require 12 volts, which operate on 12 volts. Like you have your radiator system which cools the engine, you have a radiator which cools the battery pack. And you might have seen Tesla's very nice cooling system, which provides optimum cooling efficiency in all temperatures. And finally, again, you have DC-DC converters, which help for auxiliary components. So with that being said, I think we can move to the battery types. Now, there are various battery chemistries to consider. All current cars, that is internal combustion engine cars, run on lead acid batteries, which are on the far end of the graph. Then you have nickel cadmium, then nickel metal hydride, then manganese lithium ion, then phosphate lithium ion, then cobalt lithium ion. You have varying energy densities. You have 40 for lead acid, and it goes up to 160 watt-hours per kg for lithium ion. So which battery would be the optimum choice? It is obviously lithium ion. What are the advantages? You have high energy per kg. It has a long cycle life. You have long charge and discharge cycles. You have deep discharge. You might have seen your phones even operating at 1% and 2% charge for, say, a longer time, which is say around 10-15 minutes. That is what deep discharge means. They are highly efficient in storing and returning energy. They have fast charging capabilities. I would like to, ask you all to take an analogy with your smartphones, which is exactly how the car also charges. Which is why the fast charging of your smartphones also happens in your electric car. But you need specialized equipment called DC fast chargers, which are not available at your house, which cannot be installed at your house. You would need to connect it directly to the grid, which is why there are only public DC fast chargers. So I am not very sure what the phone is, but it is some OnePlus 7 or 8, which gives you around I think 80% charge in 30 minutes or so. The DC fast chargers for, say, the Nexon can charge your charge 80% of your battery in around 30 minutes. So if you plan your journey in such a way that you start from your house in the morning, you have to reach around 500 kilometers away, you can maybe stop for lunch, get your car charged in 30 minutes, and be on your way. But that is at a DC fast charging station. Next, you also have a flat discharge curve. You have low self-discharge. Suppose you're taking your car to your airport. It's not your airport, I'm sorry. Suppose you're taking your car to the airport and you're going on a trip which takes around 3 days. So you take your car, you park it at the airport, switch it off, go on the flight, go do your stuff for 3 days. You come back, and you might notice that your 100% battery is not at 100% anymore. It would be at 90%. So this 10% is considered low. That is self-discharge. So this low sort of self-discharge is why lithium-ion chemistries, cobalt lithium-ion chemistry is preferred. And it is also maintenance free, same to your analogous to your lead acid batteries, wherein you need not check each and every cell whether the distilled water level is okay. I think Amaron provides maintenance free batteries. The same way you have maintenance free batteries for lithium ion. It is non-toxic, and you do have second life of batteries, wherein once your car reaches 5 years old, your battery has to be replaced. You can't, that same battery pack cannot be used to power a car anymore. But you can use the same battery to power an inverter. So which is why you have no disposal issues and you have a proper recycling method. Now, move on to how cells are shaped. You have cylindrical cells as used in Teslas. You have prismatic cells, which are made by Panasonic. And you have pouch cells, which mostly you will find in your mobile phones. But I think Chevrolet Bolt also uses these sort of batteries. Oh, let's move on to the disadvantages and advantages. The cylindrical cell has good mechanical stability. None of the components are scrunched together. The prismatic cells have more stress on the corners of the pack since they are bunched together. And the pouch cells have a robust and easy design. So you have good packaging density. Cylindrical cells, there's a lot of free space inside the cells. The prismatic has good as high packaging density, for a matter of fact. And the main issue with pouch cells is that they swell up. Suppose you haven't used your phone for say 2-3 years and you just kept it at the bottom of your shelf. You go see the battery after a few years, it will be swollen up. The same issue happens in a pouch cell. So even when you're designing the space for a pouch cell, you'll have to take into account the swelling which will happen, which will eventually happen in a few years. Right, coming back to thermal management, it's very easy to manage your cylindrical cells. Prismatic have very difficult thermal management problems. And the pouch cells, you must be very careful to place them far away from edges, because if you have something sharp in your suppose the bodywork of your car is too sharp, it can lead to puncture of the cells and it is obviously a fire risk. So where are they used? Cylindrical cells are used mostly in Teslas. Almost every other EV uses a prismatic cell, and pouch cells are limited to mobile phones. But the earlier first gen Chevrolet Bolt EV, obviously it's not sold in India, used the pouch cell. So I think with that we can move on to the main prime mover, which is the motor. Right, the types of motors. You have basically 5 types of motors. The most important ones are a permanent magnet synchronous motor, a switched reluctance motor, a brushless DC motor, a regular old DC motor, and induction motor. Now, I would also like to give you this table, which helps you understand easily. So now, how does the motor work? If I could just get your attention to the brushless DC motor, you have a stator permanent magnets with coils around them. This is your rotor in the middle, and you have coils. So this is one set, you could say. So when you charge, you should actually have another set here. It has not been represented because it's a cross section. So you have one coil here, and there's another one here, north south, north south. So when you energize this set of coils, this would have north and this would have south. So these would be attracted to the north south of the magnets. So while it is attracted, this will move, this will rotate. So when the south of this reaches here, these two coils will be de-energized and these two coils would be energized. So again, this becomes north. So this will be repelled by the north and this will be attracted to the south. So again, once this goes, this will also rotate. So as and when you have coils energizing and de-energizing, they move on to their respective north-south positions. The rotor rotates. So when the rotor rotates, you have your prime mover. So you have a rotor which moves, and this can be coupled up to your transmission, and the transmission can power the car. So this is a very simple concept. The same concept is also applied to the permanent magnet synchronous motor, but the main difference is that brushless DC motor is a DC motor, and this is a permanent magnet synchronous motor runs on AC. Switched reluctance is also the same, but you can't call it either an AC or a DC. It depends upon the mode of operation. So now, suppose you're designing an electric car. Which motor will you use? So let's take a deep dive into the parameters of the DC, induction motor, switched reluctance, PMSM, and BLDC. Now, in terms of power density, PMSM and BLDC are the most, with DC the least. Why? Because they are brushes. Brushes tend to spark and heat up, which reduces your power and also require frequent maintenance. Let's move on to efficiency. DC again has a low efficiency, and PMSM and BLDC have a higher efficiency. Controllability, how easy is it for you to control? DC has the most control. It's easy. You don't need complex motor control equipment. Induction motor gets a 4. Switched reluctance gets a 3. Switched reluctance motor was one of the very first motor types, brought into this world, and they require very complex control hardware, which is not available at the time, which is why at that point of time, control was low, which is why there is a lower figure here. PMSM, BLDC, they require a separate control unit, just like you have an electronic control unit which controls fuel and spark in your engine. You have a separate motor controller which controls which coils are energized and which coils are de-energized. Reliability, DC is only 3. Why? Brushes. Induction motor is 5, SRS 5, PMSM, BLDC take 4. Cost, DC is expensive, induction motor is the most expensive. PMSM, BLDC have 3. Noise level, DC is a 3, IM is 5, SR has the least noise, and PMSM and BLDC have the most noise. But most noise is relative, because electric vehicles don't make that much noise apart from that annoying whirring of the motor, which is why most manufacturers have decided to give artificial noises to the electric vehicles so that the other pedestrians and other road goers know that there is an electric vehicle coming behind them. I mean, if you would have experienced, say, electric scooters, they absolutely have no noise, and they have an instant torque curve. So right from 0, the torque is immense. So they go fast, and there is absolutely no noise with them. So it's really dangerous. Coming to maintenance, DC is a 1, and PMSM and BLDC are a 5. So which motors would you use based on this data? What informed decision will you make? You would choose a PMSM if you have an AC application, and a BLDC if you have a DC application. Now, if you ask me, if I just keep a battery in my car and a motor in my car, is that enough? Can the car go? I would say no, because you need a complex battery management system which tells you your state of charge of the battery, how much battery you have, how much individual cells have, are there any issues with the cells, and whether charging is happening correctly or not. Coming to the motor side, you need a controller, a proper separate control unit which controls the motor, which coil has to be energized, which has to be de-energized, so on and so forth. Suppose you have multiple coils like this. You can energize this positively and energize this in the negative polarity. So it helps you to, helps you in performance. It spins faster and you get a higher torque. When I say spins faster, it can spin only up to a maximum speed. It cannot go higher, as the speed cannot be as high as the internal combustion engine vehicles. The torque, yes, acceleration would be way more than petrol and diesel vehicles, but it's only up to a particular point. Suppose you want to race your Tesla Model S or Model X, and you want to race your, Lamborghini Aventador, which would eventually win. For the first half of the race, the Tesla would have smoked the Aventador. It would have gone very fast just to its sheer acceleration. And then once it reaches around 150 or no 150 miles an hour, it would continue to be in the 150 miles an hour. The Lamborghini can go all the way up to 200 or even more. So it might accelerate not as fast as the Tesla, but the speed is higher. So that speed helps out in, say, a drag race. So let's move on. Charging equipment. You might ask me, I have an electric car. How do I charge it? So let's go on to the types of charging. Right. You have an AC. This is very simple. You have either an AC charger or a DC charger. So diving deep into it, you have a level 1 charger, which is a 1.9 kilowatt charger. As you can see, the atrocious charge time of 16 hours. And how is it connected to the electric grid? Just through a residential connection, the same power line from your house. So a little more improvement is an AC level 2 charger, which is a higher capacity at 2.5, 19.2 kilowatts. And it takes around 2 to 12 hours. This 2, I feel, is a gross understatement because it's a minimum of 8 to 9 to 12 hours. The same thing is a residential connection to the grid. Now, these are all the slow chargers. You come back to your house, you plug in your electric car to the grid. The whole night it charges, and the morning you might have, say, 80% or 90% of charge left just for your commute to the office, say 40 to 50 kilometers. Then you go to your office, you again charge it the whole day, and it charges, and you have 80 to 90%, and you can use that 80 to 90% to come home, again charge, again go to office, charge. So this is a vicious circle of charging, discharging while you're driving, range anxiety, and all that. So what do? I mean, you drive a car for one pleasure and one, necessity. So this is why, just like you have, speed petrol or extra premium petrol, you have DC fast charging. So what is DC fast charging? It is a very high power, 50 kilowatt. So I'll go on to the next one also, DC high power, which is 350 kilowatt. So in a matter of 20 to 40 minutes, you can have 80% of the battery charged, and you can go on in your journey. So this is a public station. But the high power charger, like you have the Tesla superchargers, charge probably your whole battery pack in a maximum of 10 minutes. But this is directly connected to your grid. This is the only issue. So only when you have DC high power chargers, can you compare your range and performance to an IC engine? Not performance, I'm sorry, range and ease of use to an IC engine. So you might have seen you have just two pumps to put in petrol and diesel, but then there is no standard to say you must have only this sort of size and this sort of shape to your connectors. So there are a range of charging connectors. I'll show you the first AC connector. This is for North America, J1772 type 1. Japan has a different connect or same connector. The European Union has a different connector. China has a different connector. And obviously, Tesla has a different connector. So when you come to DC fast charging, you have CCS, CHAdeMO, CCS2, and GB/T. CCS2 is widely used. CHAdeMO is also used. But if you would have heard of, say, the Nissan Leaf, which are the pioneers in EV cars, they use CCS2. And Tesla obviously has its very own single plug connector for all its vehicles, apart from the European Union. So what is the final message? AC charging is slow. DC